On November 30th, 2025, Hubble photographed something that shouldn't be possible: a 60,000-kilometer teardrop pointing straight at the sun. NASA called it a tail. They were wrong. What you're looking at isn't gas or dust being blown away by solar wind. It's a swarm of solid objects, holding formation against every law of physics we thought we understood. The prediction came true within 1%. That kind of accuracy doesn't happen by accident. And here's what nobody's saying out loud yet. 3I Atlas might not be traveling alone. Stay with me until the end, because what we're about to uncover will change how you see everything moving through our solar system. The evidence is already here. We just weren't looking for it. You'll want to stay close as this interstellar stranger races through our neighborhood and the observations keep stacking up. Subscribe and follow along, because each new piece of data brings us closer to understanding what's really passing through our solar system. Now, settle in and let's unravel this cosmic puzzle together. On November 30th, 2025, the Hubble Space Telescope turned its gaze toward something that shouldn't exist. The object was 286 million kilometers from Earth, racing through our solar system on a trajectory that screams visitor. What Hubble captured that day wasn't just another photograph of a distant comet. It was evidence of something that makes scientists go quiet, then immediately start arguing. The image shows a teardrop, not a small one, not a vague smudge in the cosmic dark. This teardrop spans 60,000 kilometers of space. That's roughly 5 times the diameter of Earth. The shape is precise, almost geometric, with a bright nucleus at its heart and a massive, glowing envelope surrounding it. The whole structure points directly at the sun, like an arrow, like an accusation, like something that knows exactly where it's going. Here's the problem. Comets don't do this. You've seen comet pictures before. They have tails that stream away from the sun, pushed by solar wind and radiation pressure. It's one of the most basic rules of how these icy wanderers behave. The sun blows material off the comet's surface, and that material flows in the opposite direction, creating those magnificent cosmic streamers we all recognize. Sunward halos aren't supposed to happen. They violate the physics of solar radiation pressure. They suggest something is actively holding this structure together, maintaining its shape against forces that should tear it apart. The object creating this impossible geometry has a name: 3I Atlas. The 3I means it's the third confirmed interstellar object ever detected. The first was Oumuamua in 2017, that cigar-shaped mystery that accelerated for no clear reason. The second was Borisov in 2019, which at least had the decency to look like a normal comet. 3I Atlas arrived on July 1st, 2025, spotted by the Atlas survey system. From the beginning, astronomers knew it was just passing through. Its trajectory is hyperbolic, meaning it's not bound to our sun. It came from somewhere else, somewhere between the stars, and it's leaving again. We get one chance to study it. That nucleus, the solid core of this thing, is tiny. Hubble's measurements constrain it to 5.6 kilometers in diameter at most, maybe smaller. Picture a mountain, then picture that mountain wrapped in a glowing envelope that's thousands of times larger. The scale defies intuition. The nucleus is a grain of sand inside a basketball, except the basketball is made of something that shouldn't be able to hold its shape. Scientists thought they understood 3I Atlas. Earlier observations in July showed exactly what you'd expect from an interstellar comet. There was a dust cocoon around the nucleus, sure, but there was also a conventional dust tail forming away from the sun. Everything made sense. The object was outgassing, losing material as it warmed up approaching perihelion. Standard comet behavior for something that had spent eons in the frozen darkness between stars. The models fit, the predictions aligned. Everyone could go home satisfied that the universe was still following the rules. Then November happened. The shift is dramatic. The conventional dust tail is gone, or at least not visible in the way it should be. Instead, there's this massive, symmetric teardrop pointing sunward. The structure appears stable, coherent, and completely wrong. The halo doesn't look like gas or fine dust particles being blown around. It looks solid. It looks organized. It looks like something that's maintaining its configuration, despite everything physics says should happen to it. You can see individual stars in the background of the Hubble image. Their light streaked into lines by the telescope's motion during the exposure. 3i Atlas sits among them, sharp and clear. This alien geometry imposed on the star field like graffiti on a museum wall. The symmetry is what gets you. Nature loves chaos and disorder. Perfect shapes are rare. Perfect shapes that point directly at the nearest star are rarer still. The question forming in every astronomer's mind is simple and terrifying. What is 3i Atlas really? Is it a comet that's behaving strangely because of some compositional quirk? Is it multiple objects flying in formation, creating an illusion of a single structured thing? Or is it something we don't have a name for yet? Something that requires new categories and new physics to explain? The timing matters too. We're looking at this object right now, in late 2025, as it's making its closest approach to the Sun. This is our best and possibly only chance to gather data. In a few months, it will be accelerating away, fading from view, taking its secrets back into the interstellar night. Every observation window is precious. Every image could be the one that cracks the mystery wide open or makes it infinitely stranger. Some scientists are calling it a standard comet with unusual viewing geometry. Others are dusting off theories about swarms and distributed structures. A few are saying things in private that they won't say in public, because those things sound too much like science fiction. The gap between what the image shows and what our models predict is wide enough to fit entire new paradigms of cosmic phenomena. The promise here is this. In the next part, you're going to learn about a theory that predicted this exact configuration before Hubble even took the photograph. A theory that claims the sunward teardrop isn't gas or dust at all, but a swarm of solid objects, possibly thousands of them, traveling together in a coherent formation. The prediction and the observation matched within 1%. That level of accuracy doesn't happen by accident. It doesn't happen by lucky guessing. When a prediction is that precise, you're either looking at coincidence, so unlikely it borders on impossible, or you're looking at someone who understood what 3i Atlas really is before the rest of us caught up. What do you think happens when scientists realize they might have been looking at this all wrong from the start? There's a hypothesis floating through the astronomical community right now that sounds like something from a sci-fi novel. The sunward teardrop around 3i Atlas isn't a cloud of gas and fine dust. It's a swarm, a collection of solid micro-objects, potentially ranging from dust grain size to small boulders, all flying in loose formation around the central nucleus. Each piece maintaining its position relative to the others, creating the appearance of a coherent envelope when you zoom out. It's not a diffuse coma. It's a distributed assembly of solid fragments. The person most associated with this interpretation is Avi Loeb. You might know him as the Harvard astronomer who suggested Oumuamua could be an alien light sail. He's built a career on asking uncomfortable questions and proposing explanations that make his colleagues nervous. His analysis of the November 30th Hubble image doubles down on the swarm concept. According to his assessment, what we're seeing matches predictions that were made before the photograph was taken. The match isn't rough, it's precise, within approximately 1% of the predicted configuration. Let's unpack what that means. The swarm hypothesis predicted several specific features. First, there should be a sunward symmetric envelope with a tightly defined axis, not a vague blob, but a structured teardrop with clear boundaries. Second, The density profile should be relatively uniform across the envelope, not concentrated in jets or irregular clumps. Third, the structure should appear stable over observation periods, not expanding or dissipating rapidly like a normal cometary coma would. The Hubble image, according to proponents of the theory, shows all of these features. When a prediction matches observation that closely, you have to take it seriously. 1% accuracy is not something you stumble into with a wild guess. Either the model captured something fundamental about 3I Atlas's structure, or we're witnessing a statistical fluke of cosmic proportions. Scientists hate flukes. They hate coincidences. When the numbers line up, there's usually a reason. So what exactly is a swarm in this context? Imagine the nucleus of 3I Atlas as a parent body that's been shedding material, not as gas molecules escaping into space, but as larger solid fragments. These fragments don't drift away randomly. They maintain some degree of gravitational or electromagnetic coherence with each other and with the nucleus. You get thousands or millions of small objects, each one orbiting in the general vicinity of the central body, creating a cloud of solid material that reflects sunlight. From a distance, it looks like a halo. Up close, it would be a blizzard of rocks and ice chunks, all tumbling through space in synchronized chaos. This challenges everything about conventional cometary models. When comets outgas, they release volatile compounds like water vapor, carbon dioxide, carbon monoxide. These gases drag fine dust particles with them, creating the familiar coma and tail. But gas molecules are incredibly susceptible to solar radiation pressure. Photons from the sun literally push them away, which is why comet tails always point away from the sun. It's physics 101. You can't have a stable sunward envelope of gas. The sun's radiation would blow it apart in hours. Solid objects are different. Larger particles, anything bigger than a few millimeters, are much less affected by radiation pressure. They respond primarily to gravity. If you have a swarm of solid fragments, they could potentially maintain a coherent configuration even when subjected to intense solar radiation. The sunward teardrop suddenly makes sense. It's not being blown by the solar wind. It's being held together by the gravitational and possibly electromagnetic interactions between the fragments themselves. If this interpretation holds, the implications cascade outward like shockwaves. First, 3I Atlas isn't just one object, it's a system. The comet we've been tracking is actually a complex, multi-component assembly. Second, the total mass of the system could be orders of magnitude larger than what we'd estimate from the nucleus alone. All those fragments add up. You're not looking at a mountain anymore. You're looking at a mountain range distributed across tens of thousands of kilometers. Third, we might need to completely rethink our classification schemes for comets, especially interstellar ones. The swarm concept also raises uncomfortable questions about origins. How does a swarm form? One possibility is catastrophic disruption. Maybe 3I Atlas was originally a larger body that broke apart, either through collision or tidal forces or internal stresses. The fragments stayed loosely bound, creating the structure we see now. Another possibility is that this is how some interstellar objects naturally evolve over millions or billions of years of travel through the galaxy. Cosmic rays, radiation, thermal cycling, all gradually fracturing the surface and creating a debris field that travels with the parent body. Or, and this is where it gets speculative, maybe it's deliberate. Maybe the swarm configuration serves a purpose. If you wanted to create a spacecraft that could survive the interstellar void for eons, you might not build a single solid object. You might build a distributed system where damage to one component doesn't destroy the whole. Redundancy through distribution. It's a concept we use in engineering here on Earth. Why wouldn't it work in space? The data we have right now is suggestive, but not definitive. The Hubble image shows the teardrop. The match to predictions is striking, but we don't have close-up photographs of individual fragments. We don't have mass estimates for the swarm components. We don't have trajectory data precise enough to prove these are separate objects, rather than an optical illusion created by dust density variations. What we have is a hypothesis that fits the available evidence better than the alternatives. That's exciting. It's also frustrating, because we need more data to be sure. The scientific method demands skepticism. Extraordinary claims require extraordinary evidence. The swarm theory is extraordinary. It proposes that what looks like a comet is actually a coherent assembly of thousands of solid objects flying in formation through our solar system after traveling between the stars for who knows how long. That's a big claim. It needs to be tested, challenged, refined, or discarded based on better observations. But here's the thing. Even if the swarm hypothesis is wrong, we still have to explain what Hubble photographed. We still have to account for that sunward teardrop. We still have to reconcile the shift from conventional comet behavior in July to this bizarre symmetric envelope in November. Something changed, or something about our understanding was incomplete from the start. Either way, 3i Atlas is telling us we don't know as much about interstellar objects as we thought we did. What happens when other scientists hear about this and start proposing their own explanations? Not everyone is buying the swarm theory. In fact, most planetary scientists are approaching it with the kind of caution you'd reserve for a wild animal or an unverified tax deduction. The astronomical community is doing what it does best, which is generating alternative hypotheses at speed while simultaneously demanding better evidence for all of them. The result is a glorious mess of competing ideas, each with its own strengths and fatal weaknesses. The most popular conservative explanation involves cryovolcanic activity. The idea here is that 3i Atlas has ice volcanoes, or active vents on its nucleus, that are erupting jets of gas and dust, not randomly, but in specific directions. If these jets happen to be pointed sunward, or in some complex geometry that creates the illusion of a sunward halo when viewed from Earth, you could explain the teardrop without invoking swarms. Media coverage has latched onto this. Headlines about ice volcanoes are much easier to digest than discussions of distributed solid object assemblies. The problem with the cryovolcanic explanation is energy. Maintaining the observed halo would require sustained, powerful outgassing over weeks or months. That demands enormous mass loss from a nucleus that's only 5.6 kilometers across at most. Where is all this material coming from? How is the nucleus not depleting itself to nothing? Comets do have jets, but they're typically directional, localized, and variable. They flicker on and off as the nucleus rotates. The Hubble image shows a smooth, symmetric envelope. That's hard to achieve with jets unless you have an implausibly uniform distribution of active vents all erupting at exactly the same rate. Then there's the viewing angle hypothesis. This is the "it's all an illusion" explanation. Depending on where Earth is relative to the comet and the sun, you can get weird projection effects. Sometimes comet tails appear to point in strange directions because of perspective. The classic example is the anti-tail phenomenon, where dust particles left behind in the comet's orbit catch sunlight and appear to form a tail pointing toward the sun when viewed edge-on. Maybe 3i Atlas is just a normal comet, and we're looking at it from an angle that makes it look weird. The counter-argument is probability. Getting a near-perfect teardrop symmetry with sharp boundaries through viewing geometry alone requires a very specific alignment. It's possible, but unlikely. And it doesn't explain why the structure appears stable. Projection effects change as the viewing geometry changes. We've been watching 3i Atlas for months. The teardrop persists. That's harder to reconcile with a simple perspective trick. Some researchers are focusing on dust grain size as the key variable. If 3i Atlas is ejecting unusually large dust particles, millimeter-sized instead of micron-sized, those particles would respond much more slowly to solar radiation pressure. They'd linger near the nucleus longer, creating a more stable coma. Pre-perihelion photometry actually supports this. Observations suggest the comet is indeed producing mostly large grains, around 0.1 millimeters in diameter, ejected at low velocities of roughly 5 meters per second. That's sluggish by cometary standards. Large dust grains would explain some of the stability, but they still don't naturally form a symmetric sunward teardrop. Dust, regardless of size, should still be influenced by radiation pressure to some degree. You'd expect at least some tail or asymmetry pointing away from the sun. The Hubble image doesn't show that, or at least not prominently. The envelope dominates. The tail, if it exists, is either very faint or obscured by the viewing geometry. That's unusual even for large grain-dominated comets. The most scientifically interesting alternative doesn't try to explain the shape at all. It focuses on composition. Studies using the James Webb Space Telescope found that 3I Atlas has an extremely carbon dioxide-rich coma. The ratio of carbon dioxide to water is among the highest ever measured in a comet. This suggests the object's surface has been heavily processed by galactic cosmic rays during its long journey through interstellar space. Cosmic rays are high-energy particles that bombard everything in space. Over millions or billions of years, they can chemically alter surface materials, breaking down organic compounds, creating new molecules, and changing the volatility profile of ices. A cosmic ray-processed crust could explain the unusual composition. It might even explain some of the outgassing behavior. But it doesn't, by itself, create a solid swarm envelope. Knowing that 3I Atlas is compositionally weird is important. It tells us this object has been wandering the galaxy for a very long time, long enough for radiation to reshape its chemistry. But weird chemistry doesn't equal weird structure. You need an additional mechanism to get from unusual comet to coherent swarm of solid objects. The controversy is amplified by how different communities are covering this. Mainstream scientific sources are cautious, emphasizing the need for more data and peer review. Meanwhile, tabloids and speculative media outlets are running with headlines about alien probes and interstellar fleets. The gap between these narratives is enormous. On one side, you have sober discussions of dust grain dynamics and viewing geometry. On the other, you have breathless speculation about extraterrestrial technology. Both camps are looking at the same Hubble image, but they're seeing completely different things. This matters because public perception shapes funding and research priorities. If 3I Atlas becomes associated primarily with fringe theories, mainstream scientists might avoid studying it to protect their reputations. That would be a tragedy, because regardless of what it is, this object is giving us an unprecedented opportunity to study an interstellar visitor up close with the best instruments we've ever built. We should be throwing everything we have at it, not arguing about whether it's respectable to take it seriously. The debate also highlights a deeper issue in how we classify cosmic objects. Our taxonomy is based on solar system bodies. We have asteroids and comets, and a few subcategories for things that blur the lines. But interstellar objects might not fit these categories. They formed in different stellar environments, experienced different histories, and arrived here with properties we've never encountered before. Maybe we need new classifications entirely. Maybe interstellar comet is too simplistic. Maybe 3I Atlas is showing us that the universe is more diverse than our filing system can handle. None of these explanations are entirely satisfying. Each one answers some questions while raising others. The cryovolcanic model struggles with energy budgets. The viewing angle hypothesis struggles with probability. The large grain model struggles with symmetry. The cosmic ray processing model struggles with structure. And the swarm model, for all its predictive success, struggles with the simple fact that we've never seen anything like it before. Extraordinary claims and all that. What if the truth is even stranger than any single hypothesis suggests? The teardrop isn't the only thing that's strange about 3I Atlas. When you start looking at the details, the object reveals a constellation of anomalies that don't add up to a simple comet, even a weird one. There are patterns in the data that suggest something more complex is happening, something that spans multiple observational domains. Motion, brightness, polarization, chemistry. Each one tells a slightly different story, and those stories don't quite fit together unless you start entertaining uncomfortable possibilities. Let's start with trajectory. 3I Atlas is moving through the solar system on a hyperbolic orbit with an eccentricity well above 1.0. That's the mathematical proof that it's not gravitationally bound to our sun. It came from interstellar space, and it's returning there. The velocity is consistent with an object that's been traveling between stars for who knows how long. Millions of years, maybe. Billions, possibly. The trajectory alone confirms the interstellar origin. No debate there. But trajectories can tell you more than just where something came from. They can reveal non-gravitational accelerations, tiny deviations from the path predicted by gravity alone. Comets often show these deviations because of outgassing. As volatile materials evaporate from the sunlit side of the nucleus, they create a rocket effect, pushing the comet slightly off its predicted course. It's subtle, but measurable. The question is whether 3I Atlas's acceleration, if any has been detected, matches what you'd expect from standard cometary outgassing. Some observers, particularly those in less mainstream forms, claim the acceleration profile doesn't fit. They suggest the deviations are too precise, too controlled, as if the object is adjusting its course. This is unverified. No peer-reviewed paper has confirmed anomalous acceleration with high confidence. But the claim persists, and it's worth noting because it echoes the Oumuamua controversy, where unexplained acceleration led to speculation about everything from hydrogen icebergs to light sails. If 3I Atlas shows similar behavior, we're looking at a pattern, not an isolated incident. Then there's the fleet hypothesis. This is where things get truly speculative. Some advocates of the swarm theory claim that careful analysis of brightness variations and subtle reflections in the vicinity of 3I Atlas suggests multiple objects, not just fragments around a single nucleus, but discrete companions traveling in formation. The idea is that 3I Atlas isn't a solitary comet, but part of a group, a fleet of interstellar wanderers moving together through space. If true, this would explain a lot. Multiple objects could create the observed symmetry through mutual gravitational interactions. They could maintain coherence against solar wind and radiation pressure by effectively shielding each other. The combined mass would be greater, making the system more stable. But proving this requires resolving individual objects, which is beyond Hubble's capability at this distance. What we have are hints. Brightness peaks that don't correspond to rotation. Light curves that suggest complexity. None of it is definitive. All of it is intriguing. Polarization is where things get genuinely unprecedented. The first polarimetric study of 3I Atlas, conducted before perihelion, found a negative polarization branch with a minimum around negative 2.7% at small phase angles. That's the angle between the sun, the object, and the observer. Negative polarization means the reflected light is polarized perpendicular to the scattering plane, which is unusual. Most comets and asteroids show positive polarization at similar phase angles. The depth and sharpness of this negative polarization branch is unlike anything seen in known solar system objects. It suggests 3I Atlas's surface, or coma, has optical properties that don't match our existing catalog. Polarization is sensitive to particle size, shape, composition, and surface texture. The extreme behavior here implies a combination of factors we haven't encountered before. Maybe the grains are unusually large and fluffy. Maybe the surface is covered in exotic ices created by cosmic ray processing. Maybe the swarm hypothesis is right, and we're seeing polarization from a distribution of solid fragments with unusual shapes. Whatever the cause, The polarization data alone places 3I Atlas in a category of its own. It's not behaving like a typical comet. It's not behaving like an asteroid. It's something else, something that requires new models to explain. The chemical composition adds another layer. The James Webb Space Telescope's observations revealed that carbon dioxide dominates the coma, with a carbon dioxide to water ratio that's extraordinarily high, possibly the highest ever measured in a comet. There's also carbon monoxide, water vapor, and dust, along with tentative detections of water ice grains. But it's the carbon dioxide dominance that stands out. In most solar system comets, water ice is the primary volatile. Carbon dioxide is present, but secondary. 3I Atlas flips that ratio. This ties back to cosmic ray processing. The hypothesis is that during its long, interstellar journey, the object's outer layers were bombarded by galactic cosmic rays, which are energetic enough to break chemical bonds and rearrange molecules. Water ice could be converted into carbon dioxide and other compounds through radiolysis. Over billions of years, the surface chemistry would shift dramatically. What we're seeing now, when 3I Atlas outgasses, isn't the pristine material it formed from. It's the processed, irradiated crust, altered by eons of exposure to the harsh interstellar environment. That's scientifically fascinating. It means 3I Atlas is a time capsule, but not in the way we usually think of comets. It's not showing us the conditions of its birth. It's showing us what happens to an object during millions or billions of years of wandering between stars. It's a relic shaped by time and radiation, and its chemistry reflects that history. But here's the uncomfortable question that keeps surfacing, the one that responsible scientists whisper about in private and fringe theorists shout from rooftops. What if all these anomalies, the trajectory, the fleet hypothesis, the polarization, the chemistry, aren't random quirks? What if they're signatures of something deliberate? What if 3I Atlas is designed? The idea that an interstellar object could be artificial isn't new. We've been speculating about it since Oumuamua. The difference is that with each new anomaly, the speculation gains a foothold. A swarm of solid objects maintaining coherent formation across 60,000 kilometers of space. Unusual acceleration, extreme polarization, chemistry that suggests processing over cosmic timescales. Each piece, taken alone, can be explained naturally, but together, they form a pattern that starts to look less like coincidence and more like engineering. This is pure speculation. There is no proof, no radio signals, no artificial materials, no geometry that screams manufactured. What we have is a collection of data points that don't fit our models and a hypothesis that, while wild, isn't technically impossible. Advanced civilizations, if they exist, might send probes between stars. Those probes might use distributed architectures for resilience. They might be designed to last eons. They might look strange to observers who've only ever seen natural objects. The question is, how seriously we take this possibility. Do we dismiss it as science fiction and focus on natural explanations, even when those explanations strain credibility? Or do we allow ourselves to consider that the universe might be weirder and more populated than we've assumed? It's a tightrope walk between open-mindedness and wishful thinking. What if the next interstellar visitor looks even stranger? 3I Atlas is the third confirmed interstellar object in human history. The first was Oumuamua, detected in October 2017 by the Pan-STARRS survey in Hawaii. The second was 2I Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov, using a telescope he built himself. 3 objects in 8 years. That's our entire sample size for understanding what comes to visit us from the space between stars. It's a pathetically small data set, and yet it's already revealing that our assumptions about interstellar objects were probably wrong from the start. Oumuamua was the wake-up call. Before it showed up, most astronomers assumed that when we finally detected an interstellar visitor, it would look like a comet or asteroid, just one that happened to come from another star system. Oumuamua didn't cooperate with that assumption. It was elongated, possibly cigar-shaped or pancake-shaped depending on which analysis you trust. It tumbled chaotically through space. It showed no visible cometary activity, no coma, no tail, despite passing close enough to the sun that any ordinary comet would have been outgassing furiously. And then there was the acceleration. As Oumuamua left the inner solar system, it deviated from its predicted trajectory in a way that suggested a non-gravitational force was acting on it. The standard explanation is outgassing, but the problem is we didn't see any gas or dust. If it was outgassing invisibly, the composition would have to be exotic. Hydrogen ice was proposed. So were nitrogen icebergs. So were more controversial ideas like light sails and extraterrestrial probes. The debate never resolved. Oumuamua faded from view before we could get better data, leaving us with more questions than answers. Borisov was supposed to be the normal one. When it arrived in 2019, astronomers were relieved to find it looked like a comet. It had a coma, a tail, spectroscopic signatures of gas and dust. It behaved the way comets are supposed to behave. Finally, a data point that fit the models. Finally, proof that not every interstellar visitor is going to be a paradigm-breaking mystery. Except Borisov wasn't quite normal either. Its composition was unusual, with carbon monoxide to water ratios different from typical solar system comets. Its dust properties suggested formation conditions unlike those in the outer solar system. It was comet-like, yes, but it was also distinctly alien, a reminder that objects from other stellar environments might follow different evolutionary paths and end up with different chemistry. Now we have 3I Atlas, and it's making both previous visitors look straightforward by comparison. It has comet-like features, sure, but also this bizarre sunward teardrop swarm structure that defies simple categorization. It's compositionally extreme with its carbon dioxide dominance. It shows anomalous polarization, and depending on who you ask, it might be part of a fleet or showing signs of controlled dynamics. 3 interstellar objects, 3 completely different presentations. The pattern, if there is one, is diversity. This raises an uncomfortable possibility. What if we've been missing swarm-like features in previous visitors because we weren't looking for them? Oumuamua's data was limited. We got optical observations, some spectroscopy, trajectory data, but no high-resolution imaging of the kind Hubble provided for 3I Atlas. If Oumuamua had a distributed structure, we might not have detected it. The elongated shape inferred from light curve variations could be reinterpreted as a swarm of objects rather than a single elongated body. The lack of visible cometary activity could make sense if it wasn't a monolithic nucleus, but a collection of fragments. Borisov's data was better, but still not comprehensive. We saw a coma and tail, but did we map the structure in enough detail to rule out a swarm component? Could some of the unusual dust behavior be explained by multiple objects rather than one? It's speculative, but not impossible. Our observational techniques and theoretical frameworks are built around the assumption of single, coherent bodies. If nature is producing distributed systems, we might systematically underestimate their frequency because we're not designed to recognize them. This suggests we need a new taxonomy for interstellar visitors. The binary classification of comet versus asteroid isn't sufficient. We need categories that account for structural diversity. Loose aggregates, swarm systems, hybrid objects with both icy and rocky components, maybe even distinctions based on processing history. An object that's been wandering the galaxy for 1 billion years, bathed in cosmic rays and interstellar radiation, is going to be fundamentally different from a pristine solar system comet that formed 4.6 billion years ago and has been in cold storage ever since. 3I Atlas might be the tipping point that forces this reclassification. It combines the best observational data we've ever gathered on an interstellar object with features that can't be easily dismissed or explained away. It's not a fuzzy detection or an ambiguous signal. It's a high-resolution Hubble photograph showing something that challenges our models. That's hard to ignore. That's the kind of evidence that shifts consensus, slowly, grudgingly, but inevitably. There's also a cultural and philosophical dimension here. For all of human history, we've thought of comets as omens or curiosities, icy wanderers that occasionally grace our skies. The idea that some comets might be visitors from other star systems, carrying with them the imprint of alien stellar environments and billions of years of cosmic history, changes the emotional weight. We're not just looking at rocks and ice. We're looking at messengers from the larger galaxy, physical proof that the space between stars isn't empty, that material circulates through the cosmos, that we're connected to stellar neighborhoods we'll never visit. And if some of these visitors turn out to be artificial, or even just partially engineered, the implications cascade further. It means we're not alone. It means other civilizations have achieved interstellar capability. It means our sky might be full of probes and artifacts we've been misidentifying as natural objects for centuries. That's a paradigm shift on par with the Copernican revolution. It's the kind of thing that changes how we see ourselves in the universe. The lesson from past interstellar visitors is humility. Every time we think we understand what to expect, the universe delivers something that doesn't fit. Oumuamua was weird. Borisov was less weird, but still unusual. 3I Atlas is weirder than both. The trend suggests that interstellar objects are going to keep surprising us, that our models are going to keep failing, and that we need to develop frameworks flexible enough to handle phenomena we haven't imagined yet. Maybe the real question isn't what 3I Atlas is, but what it's preparing us to discover next. Science is full of situations where many simple units combine to create complex, coherent behavior that looks designed, but emerges naturally. Swarms are everywhere once you start looking for them. Flocks of birds, schools of fish, ant colonies, even galaxy formations. The principle is universal. Individual components, following simple rules, can generate sophisticated collective dynamics without any central control. This isn't speculation. It's documented, reproducible, and increasingly well understood through simulations and experiments. In artificial intelligence and robotics, swarm coordination has become a major research frontier over the past decade. Multi-agent systems, where dozens or hundreds of autonomous robots work together without a central controller, can accomplish tasks no single robot could manage. They self-organize into formations, adapt to obstacles, distribute workload efficiently. The individual units are simple. The collective behavior is sophisticated. Sound familiar? The mechanisms driving these systems are mathematical and algorithmic, but the emergent properties can look eerily lifelike or even intentional. A swarm of drones forming a three-dimensional lattice to inspect a structure, or nano-robots coordinating to perform microsurgery, these are real technologies being developed right now. They prove that coherent swarm behavior is achievable through nothing more exotic than local interactions and simple feedback rules. No magic required. No intelligence needed at the individual level. Just physics and programming. If human engineers can create stable swarms at scales from nanometers to meters using current technology, is it really such a stretch to imagine that natural processes operating over millions or billions of years could produce similar structures at cosmic scales? A comet nucleus fragmenting under thermal stress or tidal forces, with the fragments maintaining loose gravitational or electromagnetic coupling, isn't fundamentally different from a swarm of robots maintaining formation through position feedback. The mechanisms differ, but the underlying mathematics might be similar. there's also precedent in material science for unexpected coherence under irradiation. When certain materials are bombarded with high-energy particles, they don't just degrade randomly. They can form ordered structures, self-organize into patterns, develop layers with distinct properties. This happens in nuclear reactors, in particle accelerators, in meteorites that have been exposed to cosmic rays. The phenomenon is called radiation-induced self-organization, and it's well documented. Apply this to 3I Atlas. The object has been traveling through interstellar space for potentially billions of years, subjected to continuous bombardment by galactic cosmic rays. Those rays are energetic enough to alter chemical bonds, create defects in crystal lattices, drive surface reactions. Over time, the cumulative effect could be profound. The nucleus might fracture along weaknesses created by radiation damage. Surface layers might flake off, creating a debris field. The debris, still weakly bound to the nucleus, forms a swarm. This is a natural process. No design required. Just the inexorable action of radiation on matter over cosmic timescales. The fact that we don't see this in solar system comets is easily explained. Our comets haven't been traveling through the galaxy long enough. They've been sheltered in the outer solar system, protected from intense radiation. They're pristine. 3I Atlas is weathered, processed, transformed by its journey. It's showing us what happens to comets after eons in the interstellar medium. The cosmic ray processing also explains the chemical anomalies. The extreme carbon dioxide to water ratio isn't a quirk of formation. It's a product of radiolysis, the breaking and reforming of chemical bonds under radiation. Water ice exposed to high-energy particles can be converted into carbon dioxide, carbon monoxide, and other compounds. Over millions of years, the surface composition shifts dramatically. When the object finally warms up approaching a star, it outgasses processed material, not pristine volatiles. Polarization anomalies also have analogs in small body studies. Trans-Neptunian objects and centaurs, the distant icy bodies orbiting beyond Neptune, show polarization behaviors that don't match classical comet or asteroid profiles. Some have negative polarization branches, similar to what 3I Atlas displays. The explanation involves surface texture, grain size distribution, and compositional factors. These objects are diverse. They don't all fit into neat categories. Why would interstellar objects be any different? The point of these analogs is to show that the weird features of 3I Atlas, while unusual, aren't outside the realm of known physical processes. Swarm coordination happens. Radiation-induced transformations happen. Anomalous optical properties happen. We've seen all of these in laboratories, in computer simulations, in other astronomical contexts. The fact that they're appearing together in one interstellar object is striking, but it doesn't require exotic explanations. Nature is capable of producing complexity through entirely natural mechanisms. But here's where it gets philosophically interesting. The same mechanisms that allow natural swarms could also allow artificial ones. If you wanted to design a long-duration interstellar probe, a distributed swarm architecture would have significant advantages. Redundancy against component failure. Ability to reconfigure in response to obstacles or damage. Lower mass per unit, making acceleration easier. Greater surface area for solar energy collection or light sailing. A swarm probe would look almost indistinguishable from a naturally fragmented comet, especially at a distance. This is where science and speculation blur. We know natural processes can create swarm-like structures. We know artificial processes could create similar structures. Distinguishing between them requires detailed data we don't yet have. In the absence of that data, both possibilities remain open. The responsible approach is to pursue natural explanations first, because they're simpler and don't require postulating entire civilizations. But we shouldn't close the door on alternatives prematurely. Science works best when it considers all hypotheses that fit the evidence, even the uncomfortable ones. The analogs also suggest what we should be looking for in future observations. If 3I Atlas is a natural swarm created by radiation processing and fragmentation, there should be evidence of compositional gradients, structural heterogeneity, debris trails. If it's artificial, there might be geometric regularities, synchronized motions, or electromagnetic emissions that don't fit natural processes. Either way, more data will constrain the possibilities. The fact that 2025 has delivered breakthroughs in swarm AI, advances in understanding radiation effects on materials, and now this anomalous interstellar object feels almost like the universe is trying to teach us something. Maybe the lesson is that complexity doesn't require design, or maybe it's that design can look natural, or maybe it's just that we're finally developing the tools and concepts to recognize phenomena that have always been there, waiting for us to notice. What other mysteries are we missing because we don't have the right framework to see them? Let's recap what we know for certain about 3I Atlas. It's an interstellar object, confirmed by its hyperbolic trajectory. It has a nucleus no larger than 5.6 kilometers in diameter. It's surrounded by a 60,000-kilometer teardrop envelope pointing toward the sun, visible in high-resolution Hubble images taken on November 30th, 2025. Its coma is dominated by carbon dioxide, with the highest CO2 to water ratio ever measured in a comet. It shows anomalous polarization unlike any known solar system object, and it may or may not be part of a larger swarm or fleet, depending on which analysis you trust. That's the data. Everything else is interpretation, hypothesis, speculation, constrained by physics and probability. The swarm theory claims to explain the observations with unprecedented precision, matching predictions within 1%. The competing theories propose cryovolcanoes, viewing geometry tricks, large dust grains, or cosmic ray processing. None of them fully account for all the features. We're in the uncomfortable position of having clear observations, but unclear explanations. Meanwhile, 2025 has been a strange year for science in ways that echo the 3I Atlas mystery. Laboratories around the world have published studies showing exotic material behaviors under particle irradiation, creating ordered structures where disorder was expected. Swarm robotics has achieved new milestones in coordination and emergent behavior, with multi-agent systems accomplishing tasks that seem to require intelligence, but emerge from simple rules. Observations of other small bodies in the solar system continue to reveal compositional and optical diversity that challenges our classification schemes. There's a pattern emerging, though it might be nothing more than observational bias. We're getting better at noticing complexity. Our instruments are more sensitive. Our models are more sophisticated. Our willingness to entertain unconventional explanations has grown, maybe out of necessity as much as curiosity. The universe keeps showing us phenomena that don't fit the textbook descriptions, and instead of dismissing them as anomalies, we're starting to ask whether the textbooks might be incomplete. The philosophical implications of 3I Atlas extend beyond planetary science. If this object is a natural product of interstellar evolution, it tells us that the galaxy is full of diversity we haven't sampled yet. Every star system might produce slightly different types of comets and asteroids based on local conditions. The material ejected into interstellar space carries the signature of those environments. By studying interstellar visitors, we're essentially doing remote archaeology of the galaxy, reconstructing stellar neighborhoods through the debris that escapes them. If 3I Atlas is artificial, the implications are even more profound. It means we're not alone. It means at least one other civilization achieved the capability to send objects between stars. It means our solar system is not a pristine, isolated oasis, but a node in a network of exploration or colonization or communication that spans the galaxy. It means some of the objects we see in the sky, The ones we've been cataloging as asteroids and comets for centuries might be artifacts, probes, relics, messages in bottles cast into the cosmic ocean by beings we'll never meet. Both scenarios are humbling. Either the natural universe is vastly more complex and creative than we've given it credit for, or we're surrounded by evidence of other intelligences, and we've been too parochial or too cautious to recognize it. Either way, our place in the cosmos shifts. We're not the measurers of all things. We're students, stumbling through a curriculum we barely understand. The practical question is what we do next. 3I Atlas is leaving. Its closest approach to the sun already happened. It's accelerating outward, back toward the interstellar void. Every day it gets fainter, harder to observe. We have months at most before it's beyond the reach of even our best telescopes. This is our window. If we want to understand what it is, we need to maximize observations now. That means coordinating every available instrument. Ground-based telescopes for continuous monitoring, Hubble for high-resolution imaging, James Webb for spectroscopy, radio telescopes for any possible emissions. We need multi-wavelength data, time series photometry, polarimetry, everything we can throw at it. The science community is mobilizing, but resources are limited, and competition for telescope time is fierce. Not everyone is convinced 3I Atlas deserves priority over other projects. There's also the question of future preparedness. 3I Atlas was discovered by a survey system designed to detect near-Earth asteroids and comets for planetary defense. It worked, but it was luck as much as design. If we want to systematically study interstellar objects, we need dedicated, rapid response capabilities. Telescopes that can be quickly redirected to new targets. Spacecraft on standby that can launch on short notice to intercept visitors. Data pipelines that can process observations in real time and coordinate global follow-up. Some researchers are already proposing missions. Fast flyby spacecraft that could reach 3I Atlas before it leaves the inner solar system. Rendezvous missions that would match velocity and pace the object for extended study. Even sample return, though the engineering challenges are enormous. The political and financial will for such missions is uncertain. Interstellar objects are rare, unpredictable, and fleeting. It's hard to justify standing infrastructure for targets that appear once or twice a decade. But the potential payoff is extraordinary. A single close-up photograph of the swarm structure, if it exists, would settle the debate instantly. A chemical analysis of the nucleus material would tell us about formation conditions in another star system. A mass measurement of the entire system would constrain models of fragmentation and coherence. These are questions we can't answer from Earth-based observations alone. We need to go there. The cultural conversation around 3I Atlas is also shifting. What started as a technical discussion among planetary scientists has leaked into public consciousness. People are asking questions. Is it a comet? Is it a swarm? Could it be alien? The gap between what scientists know and what they're willing to say publicly has never been more apparent. There's fear of being wrong, fear of ridicule, fear of sensationalism. But there's also excitement, because this is the kind of mystery that makes people care about science. The ultimate question is one we can't answer yet, and maybe never will with certainty. Is 3I Atlas a rare natural relic, a comet transformed by billions of years wandering the galaxy, fractured and processed by radiation into a coherent swarm of fragments? Is it a cosmic fluke, a perfect alignment of unusual factors that produces the illusion of structure where none exists? Or is it something else entirely, a probe or artifact from another civilization, designed to survive the interstellar crossing, now passing through our solar system on a mission we can't begin to guess? The honest answer is we don't know. The exciting answer is we might be able to find out if we act quickly and think creatively. The cautious answer is that extraordinary claims require extraordinary evidence, and we don't have that yet. all three answers are true simultaneously. That's the nature of frontier science. You live in the uncertainty, you pursue the data, and you resist the temptation to close the question before the evidence is in. But here's what we can say with confidence. 3i Atlas has shown us that interstellar objects are not just icy rocks following predictable paths. They're complex, diverse, and stranger than we expected. They carry information about the galaxy encoded in their composition, structure, and motion. They're opportunities to study processes and environments we can't reach any other way. And they're a reminder that the universe still has the capacity to surprise us, to present phenomena that don't fit our models, to force us to expand our understanding or admit our ignorance. 3 interstellar visitors in 8 years, each one different, each one challenging our assumptions. The pattern suggests we're only beginning to see the diversity that's out there. Maybe the next visitor will be even more anomalous, even harder to explain. Maybe it will be the one that finally proves, one way or another, whether we're alone. Until then, we watch, we measure, we argue about interpretations and demand better data. We live in the tension between what we can observe and what we can prove, between the evidence that's suggestive and the certainty that's elusive. 3i Atlas is leaving, fading back into the darkness between stars, carrying its secrets with it. The question isn't whether it will change what we thought we knew. It already has. The question is whether we're ready for what comes next.